Hi friends, welcome to another video lecture of this course. We have to study a theorem and its proof. The statement of the theorem is the non-zero vectors v1, v2, etc. till vn are linearly dependent if and only if one of them, say vi, is a linear combination of the preceding vectors represented as vi is equal to a1 v1 plus a2 v2 plus etc. till ai minus 1 into vi minus 1. Proof is very straightforward. Suppose vi is equal to a1 v1 plus a2 v2 plus etc. till ai minus 1 into vi minus 1. Then I can write a1 into v1 plus a2 into v2 plus etc. till ai into vi minus 1 plus minus 1 into vi is equal to 0. I have taken this vi to the right hand side and then equated that to 0. Then I have a1 v1 plus a2 v2 plus etc. till ai minus 1 into vi minus 1 plus minus 1 into vi plus 0 into vi plus 1 plus 0 into vi plus 2 etc. till plus 0 into vn is equal to 0. I have added zeros. I have added zeros multiplied by vi1 plus 1 plus 0 into vi plus 2 etc. so on and so forth etc. up to plus 0 into vn is equal to 0. And here all ai's are not equal to 0 as the coefficient of vi is equal to minus 1. Hence we conclude that v1, v2 etc. up till vn vectors are linearly dependent. Or I can go about in a different way. Suppose v1, v2 etc. up till vn are linearly dependent vectors, then there exist scalars a1, a2 etc. up till an which are not all equal to 0. But I have a1 v1 plus a2 v2 plus etc. up till an vn is equal to 0. Now let me assume k to be the largest integer such that ak is not equal to 0 and ak plus 1 is equal to ak plus 2 is equal to etc. up till an is equal to 0. Then I have a1 v1 plus a2 v2 plus etc. up till ak vk is equal to 0. Now let me assume k is equal to 1. Then a1 is not equal to 0, but a2 equal to a3 etc. up till an is equal to 0. And a1 v1 is also equal to 0. So that's why this implies v1 is equal to 0 because a1 is not equal to 0, and this gives contradiction as v1, v2 etc. up till vn are non-zero vectors. So therefore k should be greater than 1. And since ak is not equal to 0, I have vk is equal to minus a1 by ak into v1 plus minus a2 by ak into v2 plus etc. up to plus minus ak minus 1 by ak into vk minus 1. So I have the inference that vk is a linear combination of its preceding vectors only. Now we shall prove some results based upon the basis in a vector space. The statement for the first theorem goes like this: the set B is equal to v1, v2 etc. up till vn is a basis of vector space capital V. Then every vector w belonging to V can be uniquely expressed as a linear combination of vectors v1, v2 etc. up till vn. If the set B is equal to v1, v2 etc. up till vn is a basis of vector space V, then every vector w belonging to V can be uniquely expressed as a linear combination of vectors v1, v2, v3 etc. up till vn. Proof is very simple. Let B be a basis and w be written in two different ways. That is, w is equal to a1 v1 plus a2 v2 plus etc. up till a and vn. So here I have expressed w in terms of a. Now let me express w in terms of b. That is, w is equal to b1 v1 plus b2 v2 plus etc. up till bn vn. Then I can write, I can equate these two equations. That is, a1 v1 plus a2 v2 plus etc. up till an vn is equal to b1 v1 plus b2 v2 plus etc. up till bn vn. Transposing this right hand side to the left hand side and taking common factors, I can write this as a1 minus b1 whole into v1 plus a2 minus b2 whole into v2 plus etc. up to an minus bn whole into vn is equal to 0. But since v1, v2 and vn etc. up till vn are linearly independent, so I should have a1 minus b1 is equal to 0, a2 minus b2 is equal to 0, etc. up to an minus bn is equal to 0. Or I can write a1 is equal to b1, a2 equal to b2, etc. up to an is equal to bn. So that's why W can be uniquely expressed as a linear combinations of V1 to V1, V2, etc. till Vn. So this completes the proof of it. Okay. Now we shall go for the next important property or theorem. Any finite set S which spans the entire vector space V contains a basis. In particular, any finite dimensional vector space has a basis. So let S be equal to V1, V2, etc. up till Vn, and S spans the entire vector space V. So if S is linearly independent, then definitely it will be a basis of the vector space V. Now, if S is not linearly independent, then it means that S is linearly dependent. So in that case, there exists a vector, say Vi, which is a linear combination of its previous or preceding vectors. So I can write Vi to be Vi in terms of its preceding vectors as Vi equal to A1 V1 plus A2 V2 etc. plus etc. up to A minus 1 Vi minus 1. Or I can say S1 is equal to V1 V2 etc. up till Vi minus 1 comma Vi plus 1 etc. up till Vn, which still spans the vector space V. So if S1 is so if set S1 is linearly independent, then S1 will be a basis. This is the definition of a basis which we have studied. So if S1 is linearly dependent, suppose, then there again exists a vector, say Vk, which is a linear combination of the preceding vectors. So I can write Vk is equal to B1 V1 plus B2 V2 plus etc. up to Bk minus 1 into Vk minus 1. Or I can write S2 is equal to V1 V2 etc. up till Vk minus 1 comma Vk plus 1 comma etc. up till Vi minus 1 comma Vi plus 1 Vi plus 2 etc. up till Vn. So this still spans the vector space V. So that's why if S2 is linearly independent, then it will become a basis. Suppose if S2 is not linearly independent, right? We continue the same process until we get a linearly independent set of vectors, which will then span V and hence would be a basis of V. Okay. So in the after we repeatedly repeat this process, then it would be consisting of a independent set of vectors, which will then span V and hence would become a basis of V. So this completes the proof of the second one. Now we shall go for the third one. Let V be a finite dimensional vector space. We call it as FTVS usually. So let V be a finite dimensional vector space. So any linearly independent set capital L can be extended by adding elements to get a basis. So let capital L be equal to V1, V2, etc. up till Vn be the set of linearly independent vectors. So if L spans V, right, then each vector of V can be expressed as a linear combination of the vectors V1, V2, etc. up till Vn. So that L forms a basis itself. If L does not span V, then we have V belonging to capital V, but V cannot be expressed as a linear combination of the vectors of L. Then I need to write L1 is equal to L comma V, which is equal to V1 comma V2 etc. till Vn comma V. This is again linearly independent. So if L1 spans V, then L1 will automatically become a basis of V. Otherwise, let there exist some W belonging to V such that W cannot be expressed as a linear combination of elements of L1. Then L2 can be written as L1 comma W. Then I introduce a set L2 is equal to L1 comma W, which is again linearly independent. So if L2 spans V, then L2 will be a basis of V. If not, we need to continue the same process till we get a set, say capital S, which spans V. And of course, S would be a linearly independent and form a basis of V. Okay, so this completes the discussion of the theoretical aspects. Please practice these properties. They are very, very important. Thank you.